In this screencast, I'd like to address correlation analysis. This is a statistic that you're probably familiar with. Correlation analysis produces a measure of association known as Pearson's correlation coefficient, or Pearson's R, lowercase r, that gauges the direction and strength of a relationship between two interval level variables. It's a very useful summary of a relationship. Regression, which will be addressed in future screencasts, produces a statistic, the regression coefficient, that estimates the size of the effect of the independent variable on the dependent variable. It also produces other useful statistics. Let's talk about Pearson's R here. As you probably know, Pearson's R can range from -1, which would be a perfectly negative relationship between two variables, to +1, which is a perfectly positive relationship between two variables. Correlation coefficient near 0 or around 0 signals no relationship. As you change the independent variable, you're not changing the dependent variable. Now let's start here with this. I've found that correlation is always it does well to visualize it. This shows a scatter plot of the relationship between, for each state, each of these dots represents a state, the percent of the state's residents who have a college education or higher, so it's a measure of education along the x-axis, and turnout in the 2012 presidential election, which is represented on the vertical axis. You can see these are all in units of measure, percent college or higher, percent turnout. So for example, we know, just to give you a feel for the data here, Oklahoma, for example, has a resident population with 23% have a college degree or higher, and its turnout was 49% in 2012, so that's Oklahoma represented right there. Colorado, by contrast, has about 36% of its residents have a college education or higher, and its turnout was up here a little bit more than 70%. So that's Colorado there, that's represented there. Now, we could go ahead and characterize all the states so you can get a feel for it, but correlation analysis, the correlation coefficient doesn't rely on what are called units of measure, percentage college or higher, or percent turnout. The correlation coefficient relies on z-scores. Now this pattern is identical. The states are in the identical positions that they are in this pattern, but now their scores, their percentages in terms of college or higher and turnout, have been converted to z-scores. Now, what does this mean? We talked about z-scores back in chapter 6. Any state whose level of college education or higher places it at the mean of all states on this would have a z-score of 0 on college education. So I happen to know that the overall mean of college education or higher is 27%. So these states right here have about 27% of their residents have a college education. The overall mean of turnout was 60%. So 60 here is represented by 0 because any state that had a turnout of 60 is sitting right on the mean for turnout. So just to locate our two states that we're following here, Oklahoma, with 23% of its residents have a college education or higher, places it at about -1, about -0.9 on education, and its turnout places it at -0.16. So there's Oklahoma again, converted from raw numbers to z-scores. Similarly, Colorado, with its level of education up here at about 1.8 in terms of 1.8 standard deviations above the mean for education, and then also at about 1.6 standard deviations in turnout. So there's Colorado right there. The correlation coefficient is derived rather simply by after converting all the cases to z based on the mean and standard deviation, finding out how many standard deviations each case is above or below the mean. The correlation coefficient is computed by the cross products. So for example, we would multiply the negative for Oklahoma here, which is a -0.9, times another negative, -1.6 over here. When you multiply a negative times a negative, you get a positive. So all the cases down here are consistent with a positive correlation because negatives times negatives are positives. Similarly, all the cases up here above the mean in both variables are associated or would contribute toward a positive correlation. A positive times a positive is a positive. But the offsetting quadrants, the states that are, I guess you say, are not cooperating with the relationship, you're multiplying a negative times a positive, getting a negative cross product here, and also a negative cross product down here. Here's the formula. Here is the standardization that I've been emphasizing. For in terms of education, you would subtract the mean of the overall mean of education, the college education or higher, from the individual state's value, and divide that by the standard deviation of education to convert that raw difference to units of z, of standardized units. And you do the same for that case as values on y. yi, the individual observation of y, minus the mean, divided by the standard deviation for y. So the formula says to do that for each case and to multiply those, get what are called cross products, add all those cross products up, and then derive the average, more specifically, the number of cases minus 1, n minus 1. And when you do that, you get the correlation coefficient. Let's just review that. Convert each x value to a z-score and convert each y value to a z-score. Above the mean values of x will have positive z-scores. Below the mean values will have negative z-scores. Multiply the x value z-scores by the y value z-scores. That's, again, those are the cross products. Add them all up and divide by n minus 1, and you've got the correlation coefficient. Again, to review, cross products in the lower left quadrant produce positive values. Why? Because a negative times a negative equals a positive. Cross products in the upper right quadrant produce positives because a positive times a positive is a positive. Upper left and lower right quadrants produce negative values, weakening the positive correlation of the relationship. For the relationship we just looked at, the Pearson's R is plus. We knew it was positive because of the way the scatter was arranged. 0.43. So you can, in your mind's eye, you can think of a scale that ranges from -1 through 0 to +1. And this relationship, I guess, is moderately strong at 0.43. There are some limitations of correlation. It's very useful during the early stages of research when you want to get an idea about the overall relationship between two variables. So say you've got 5 or 6 variables that you're interested in analyzing and maybe modeling causation for a dependent variable. And correlation analysis gives you a really quick and useful sort of introduction to your variables, to the overall relationships between variables that you're going to analyze. The problem with correlation analysis is that you cannot attribute causation based on correlation. Correlation coefficient is what's called a symmetric measure of association. The correlation between, if we had turnout on the x-axis and percent college on the y-axis, it would produce the same correlation as having education on the x-axis and turnout on the y-axis. And it is not a PRE measure of strength between two variables. There is such a measure called R-square, which is produced in regression analysis, and that will be the next topic of conversation.